Saturday bi-weekly fortnightly series where we have our sessions on quantum computing related from the industry's best on their subject areas, right? We value your contributions, cooperations on joining these sessions, giving us feedbacks in terms of what next that you would like to hear from on these series. About MyQT, My Quantum Technology is a company based out of Bangalore and working closely only on software trainings, right? Quantum computing trainings and innovation solutions. I welcome Aniruddha Vishwas, our speaker for the day on quantum optimization. And he is a physics master in physics from University of Calcutta and currently working as research engineer, LTI MindTree. I welcome you, Aniruddha, for this session and looking forward for a great session on optimization. Thank you. Handing over to Aniruddha.
Yeah, thanks, Pradeep, for this intro. So, okay, so today's topic is about, although the title is Quantum Optimization, the Formulation Approach, the basic idea is basically we know what optimization problems are. Probably there are a couple of areas where quantum optimization algorithms are really performing well. But the today's session is basically to, okay, so let me share my deck first. Okay, so just confirm me if it is visible. Is it appearing full screen? Hello?
It's not it appearing.
Not it.
Not started.
Okay. Okay, is it visible? I mean, is my screen
Yes.
visible?
Yes.
It is
Yes.
visible now. Yeah.
Okay,
Yes.
so okay, so okay, so is my PPT appearing full screen or like semi-full or what? Is it appearing full screen?
Yes. It is full screen.
Yes.
Yeah. Okay. So yeah. Okay. So yeah. So title of the talk is basically there are different areas of quantum computing. So now, what quantum computing or quantum technology is all about. So before getting into all those things, let me just clarify the agenda first. So basically, so I'll be talking about mainly a couple of points that I've mentioned here. You can see that a very broad perspective about quantum computing application areas, then optimization problems, then combinatorial optimization problems. That's kind of a sweet spot for the quantum computing, and then quantum optimization workflow, and then Ising-Hamiltonian QOs, and a couple of examples on that. So now the thing is what exactly the talk is all about. So there are a couple of application areas of the quantum. So what are those basically? So as we know, the quantum computing is quite different than the standard way of classical computing, right? So because here we have already, I think the people who are attending this session, they are quite aware of this, that how quantum computing is different than the classical computing part of it. In classical computing, we talk about zeros and ones. In quantum computing, we talk about 0-1 superposition, and there are properties like superposition, interference, tunneling. Okay, so these are the properties which makes quantum computing much different than the classical computing. Okay, and because of these things, there are places where we may find quantum advantage. Probably not right away, right now. Probably in the upcoming years, definitely we'll be getting it. Okay, as the hardware improvements are going on day by day, different architectures are coming up. So there are different application areas are also emerging up. So mainly the three application areas you can think about when we talk about quantum computing application areas. So in quantum technology, there are different areas as well. Like quantum computing is one of the application side of the quantum technology. So there are other areas of quantum technology, right? So there are sensing, okay, so there are cybersecurity, cryptography, those kind of stuff. In quantum computing, they are mainly, if you just categorize it, there will be three different parts. Like one of the things will be machine learning, quantum optimization, and simulation. So in every single area, so there are, I'll be talking very less about all these three in a minute, and then jump into what exactly thing is our agenda today. So uh, so when we talk about quantum machine learning, so the term is having mainly two kind of meanings. I mean, if you just see the research groups who are working on this side, you may find there are two mainly groups. So one is basically doing machine learning to improve quantum computing, right? So what are these kind of things? Is right, basically, so suppose you are using some machine learning algorithm to denoise your hardware, okay, this kind of stuff. Another thing is basically quantum machine learning. So basically, this is a part where most people talk about this part, second part. So this is what? So this is quantum assisted machine learning. So you want to do machine learning, you are taking advantage of taking the power of quantum computing to improve your machine learning in terms of accuracy, in terms of speed, or probably whatnot. There are a lot of improvements are possible in terms of representation, data, sampling rate, whatever. So mainly, if we just mention a couple of sub areas of machine learning where quantum computing can be really useful. Those can be probabilistic sampling, combinatorial optimization. Sorry, I shouldn't mention this combinatorial optimization over there. I think classification, sometimes iteration tasks, time series modeling, those are very much important. And then comes to simulation. So in simulation also there are two areas broadly which we can classify them into. One is basically like quantum simulation. So what we talk about when we talk about quantum simulation, what exactly we just want to mean? So quantum simulation is basically suppose a system is inherently quantum. So what systems are inherently quantum? Like let's consider a chemical system. Okay. Suppose you would want to design a molecule. Okay. So that's inherently a quantum system, right? So now there are two ways to simulate it. Okay. I mean, till now, there are a lot of methods like density functional theory or many computational way of doing it. But those are the things on the classical computer. You are mimicking the quantum behavior on a classical computer. Now, these things can be speeded up in the using quantum computing. So these are called quantum simulation. So there is another meaning of another part of the simulation, that is quantum enhanced simulation. So what are those things? So let's consider that you have a really suppose you want to simulate weather, and for weather simulation you need to solve a really complicated differential equation, right? So now you know that the accuracy of differential equation the result of the accuracy of the result of the differential equation depends upon the discretization of the variable, underlying variable. Now the thing is, now if you just increase the discretization very much, you will see the performance of your classical compute is very less.
Aniruddha,
Okay.
KG here.
Yeah.
Participants are not able to view your screen. Can you stop
Okay.
sharing and then share again, please?
Yeah,
Sorry for the
sure.
confusion.
Yeah, sure.
Thank
you. I'm sharing in my entire screen. Is it visible?
Yes.
Yes, it is visible to me. What about others? Please raise your
Please
hand
confirm.
or put message in chat window. Yeah, thank you.
So is it visible to everyone?
Yes, it's visible. It's
Yeah.
visible.
Okay.
Okay.
Yes, Aniruddha.
Yeah. So the second part of the quantum simulation is basically quantum enhanced simulation. So it means that you want to simulate something, probably through some differential equation. Now you want to basically use quantum computer to do your simulation faster or more accurately. Oh, okay. So this is another part of it. So basically, when you talk about simulation, is empowering quantum computing. Quantum computing is empowering simulation. Basically, two things we talk about. One is quantum enhanced simulation technique, and the second thing is the simulating quantum system. Okay, so these are the two areas. The third thing, which is somehow today's topic, is around that is quantum optimization. So it's basically there are quantum optimization algorithms. So a couple of algorithms are there which are very good for solving quantum some optimization problem. Okay, so there are a lot of different algorithms are there. Anyway, so I'll be talking about a couple of them in a minute. So areas like financial service, supply chain, work scheduling, okay, sometimes financial portfolio optimization. So these are the areas where quantum computing can be very beneficial. Okay. So now talking about, so what is basically a mathematical optimization problem, and what are the classification areas, or what are the basically different classes of it? Okay. So suppose, so let's talk about a sample mathematical optimization problem. So there are a lot of example I can pull. So I think people, whoever attending here is pretty much aware of a problem called traveling salesman problem, right? So what is the traveling salesman problem? So there is a person who wants to visit certain city. Okay, so you can see here on the right hand side. So there are 7 or I think 6 cities I have mentioned here using some dots and lines. So basically this is a graph representation of the problem. The problem is basically the person wants to visit all the cities, okay, and come back to the same starting point within a shortest path. Now, apparently the problem looks very simple, but once you increase the number of cities, the problem becomes like intractable or computational really intensive. Okay, so with uh, so I'm not able to recall exactly what is the number of possible solution when you basically having a number of cities, but actually it grows up exponentially, and because of that thing, the problem becomes really intractable for any classical computer. Okay, so this is one of the problem when we talk about an optimization problem. So there can be a lot of optimization problem, right? So there is let's consider that you are doing machine learning, right? So in machine learning, you have a regression problem. Okay, so there are a lot of areas where you apply machine learning regression algorithm, and so at the end of regression algorithm, what you get? You get a value. Okay, you get a value. So now, what exactly you want? You want to predict the value accurately, and to do that, you define an error function, and basically you want to minimize that error with respect to your data, and basically while minimizing the error you get a better prediction accuracy, right? So this is one of the optimization problem that you can see that which is happening in the uh, through an error function of it. Okay, so usually there are a lot of error function we talk about, sometimes mean squared error or mean absolute error, they are kind of some of them. Okay, so now if you want to classify those, mainly those, what are those optimization problem classes? Okay, so mainly they fall under two classes, either discrete and there is a continuous. Okay, so in continuous you also will be able to see there is a linear as well as non-linear. In non-linear you can break them up into convex and as well as non-convex things. Okay, so in the discrete there are combinatorial optimization, which is somehow today's topic of interest, and something is the integer programming problem. Okay, now the integer programming problem also can be broken down into two parts. One is the non-linear as well as the linear part of it. So I'll not be getting into all of them in detail. So rather I'll stick, I just limit myself within the combinatorial optimization space, because that is what is called quantum optimization sweet spot. Okay. So what is a combinatorial optimization problem? So as I have already given some example, this TSP problem is a inherently a combinatorial optimization problem. So basically you have some set of options, okay, or some set of finite solutions. I would say set of finite I think points or finite sample spaces. Out of them, you have to select some depending upon some criteria, which will minimize or maximize some of the target outcome. Okay. So, and couple of problems are, I mean, some additional points regarding those problems are, these problems can be converted into graph problems, and all of them fall under some NP class, non-deterministic polynomial class. Okay, so there are also some subdivision of this, NP hard, NP complete. So these are some of the individual problems. So a couple of examples like max cut problem, Boolean satisfiability problem, knapsack problem, graph partitioning problem. Okay, now these are some kind of a problems which falls under combinatorial optimization class. And then one more thing is about, so this optimization problem are classical in nature, completely classical in nature, but there is a good way that we can just convert this problem in such a way so that quantum computer can address these problems. Okay, and the good thing is about gate-based and handling based quantum computers can handle this problem really well. So let's start talking about the other part of it. So let's now understand what is the workflow of a quantum optimization solver. Okay, so because today's talk is mainly about like how to formulate a problem in for quantum optimization, so quantum algorithm can solve it, right? So as the title mentioned, the same thing. So there are mainly 5 stages of it, as I have mentioned here in this. Okay, let me. Yeah. So hope my point is visible to everyone. So there are 5 main areas of it. You can see in this pyramid of kind of structure. You can see. So first thing is basically a problem statement, which depends upon the domain of the problem of interest. It can come from the supply chain, it can come from the material science, pharmaceutical, banking and finance, a lot of other areas as well. And the second thing is basically, so once you have the basic problem statement, you have to convert or basically formulate a mathematical version of the problem statement. Okay, so that's basically a very crucial part of it. Because whenever you are having some optimization problem, you know what the problem is, but a system doesn't know what the problem is, right? So what you have to do is have to mathematically model the problem in such a way so the system can understand that thing. And we'll be doing that thing using some QO form that is called quadratic unconstrained binary optimization class. And then we'll be doing one more step, basically quantum encoding, or basically converting the mathematical model into a quantum form so that a quantum computer can understand, because whatever the mathematical model that you have created, that is not something what quantum computer can understand. So you have to make that problem convert the problem in such a way so you get a quantum native version of it, right? And once this part is done, then the next part is basically applying some algorithm on a underlying hardware. Also, you can think of a simulator. So as we're talking about quantum optimization problems, so there are mainly 2 kind of devices you get, as the gate-based devices or annealing-based devices. So in annealing-based devices, you see that D-Wave is there, some quantum-inspired devices like Fujitsu digital annealing device, then Hitachi's device, Toshiba's simulated bifurcation machines, those are there. You can see that I have mentioned over there. You can also find a couple of algorithms, okay? Quantum inspired algorithms are also there. I think Microsoft is having a really good collection of those. And also some gate-based devices are also, algorithms are also there, like variational quantum eigensolver, quantum approximate optimization algorithm. And these algorithms can run on the devices like IBM quantum computer, IonQ, Pascal, Honeywell quantum computer, right? So, so the workflow is basically this. So basically it starts with a problem statement, and what you have to do is basically you have to formulate the problem in such a way so that a quantum computer can understand it. And once that is done, then you can simply send the problem to some algorithm, and the algorithm will be executed on some hardware, and you'll be getting the result out of it. And your problem will be solved. Probably just need to have do some kind of a post processing before extracting the output. But these are mainly the basic steps. So today's session is not about any specific algorithm. Like I'll not be talking about any VQE or QVOA or quantum annealing. That I will be talking about mostly mathematical modeling and the quantum encoding of it. So how to formulate a problem and how to convert those problems in such a way so that a quantum computer can understand, right? So this is the main agenda of it. So as I've already given you some examples that what exactly kind of problem that we are talking about. We are talking about mainly combinatorial optimization kind of problems, and TSP is one of the class, and that's basically some NP class problem. So, but the examples that I have today, they don't fall. I mean, they are not from the NP class problem. They're very easy problem to solve. But still, those problems will give you some understanding of it, that how to formulate those problems for a quantum computer. So if you're having some problem, then how to reformulate those or formulate those so a quantum computer can understand it, right? So now let's come to a standard problem, right? So now when we talk about some optimization problem, so definitely there is some objective associated with it, right? So either we want to maximize the objective or we have to minimize the objective or anything like that, okay? So let's consider that you have a knapsack problem. So there are a couple of substances are there with specific weight and value. So and your sack is having some kind of a capacity in terms of weight. So you want to get the maximum value out of it without exceeding the weight limit of your bag or something like that. Okay, so that is one kind of thing, one kind of a problem. The objective is you have to get the maximum value. Of course, there can be some additional constraints, okay, depending upon the problem. And then real life problems, you will see there are a lot of constraints are there. So those usually you have to address when you are basically formulating a problem. So let's basically start with some problems. So here you can see that a mathematical expression that we have here, basically f of x naught, x1, and x2, that's basically a binary polynomial of second degree, you can see. So basically minus 4.4, 0.6, minus 2 to 0.8, and some expression that we have. I mean, it's a three variable problem, but I mean, only 6 terms are before going into deep detail. So KG, am I audible? Because I'm not able to
Yeah. No, yes, Aniruddha.
see any authority.
I'm hearing you. Do you hear me?
Yeah. Okay. Yeah, sure.
Yeah,
Yeah.
good.
So
We are hearing. Yeah.
optimization problem. So the condition of the problem is this x naught and x1, x2, or x naught. So all these are binary. So either they can have 0, all these x can have either 0 or 1. Okay, so it means, so how many possibles are possible? How many combinations are possible? So there are 8 possible combinations with 3 bits. So this x1, x0, and x2, these are, I mean, binary. So it means there are only 2 possible combinations are available for each of these x. And for all 3, there are 8 possible combinations, starting from 0, 0, 0 up to 1, 1, and 1. And within there are 8 combinations are there. So what do we have to find out? So what is the best combination for which the value of this f of x gets minimum? Okay, so now what you can do, so as there are only 8 combinations, you can simply basically put one combination inside the mathematical expression and get the value, and you can do this for all the 8 combinations and finally get the value, and which from that you can easily find out that what is the minimum value that you have, okay, while doing it. So, but this is a very easy problem to solve. So we don't need any quantum computer for that. But while talking about TSP problem, 6 cities TSP problem or 7 city TSP problem, you definitely need quantum computer, right? So I mean, you can use definitely a classical computer to solve it or classical algorithms to solve it, because there are a lot of algorithms are there in classical space. So okay, there can be similarity handling, there can be genetic algorithm, some very branch and bound. There are very sophisticated solvers are also there, which basically kind of the wrapper around this underlying algorithm. Some Gurobi, C-Plex, these are also kind of something you can get. But I mean, there are also challenges. There are also limit of those classical solvers or of the classical algorithm. So, but just to for the understanding of the simplicity, we have taken a 3 variable problem, which is quite easy to solve. You can do that thing in your hand. So there is no need of quantum computer or classical computer to solve this thing, but you can still have some understanding that how this thing works. Okay, so and you can see there is a matrix or the table form, a 3x3 thing that I have kept here. So and this I have a mathematical expression that is binary polynomial that can be represented in this one, in this table. Okay, it's a very similar form. Basically, we call it a cubo matrix. This is basically quadratic unconstrained binary optimization problem we talk about. So you can see this. Okay, so I have actually mistakenly I have just named them x1, x2, and x3. They should be x0, x1, and x2. So, but you can think that these are x. This is x0, this is x1, and this is x2. So how we are getting this matrix from this expression? So we can see this minus 4.4 is basically, this is basically lying in the cross junction of this x0 and x0. And similarly, if you do all the stuff, and you will get this expression or the matrix. This is called cubo matrix. Okay, and this is basically a very concise representation of the problem, binary polynomial. You can get some other representation of the problem as well. That will be definitely talking about. So the thing is, this particular thing is having 8 possible solutions. Okay, now the thing is, the agenda is to find the best solution for which we get the minimum value of this expression, right? So now we'll switch back to one of my notebook that I'm having here with me, just to give you some understanding that what are the possible solution and which one is the best solution. Okay, so is my notebook visible to everyone?
Yes, Aniruddha, I'm saying.
It's
Yeah,
visible.
okay, okay.
Everyone is saying, yeah.
Yeah, so you can see that this is something that you have here. So the same mathematical expression I have written here. Okay, so let me. So the same mathematical expression you have here. So this one. Okay, the same thing. And these are the 8 possible combinations you can see on the left hand side. And what are the possible combinations? Okay. Yeah, of things are quite visible. So these are the possible combinations. I'm starting from, okay, so these are things in reverse order, starting from 000 up to 111. And these are the value of this expression or the f of x that we get if we just replace each of this thing on this, sorry, if we just put each of this bit string in this expression. So we get, for 111, we get 0.4. For 000, we get, I think, minus 1.4. Yeah, minus 1.4. And all the range of values that we get. And we can easily see, so for 010, that's the best bit string, because for that we are getting -4 answer. Okay, and -4 is the minimum of all of these which are available in this table for all the 8 combinations. And so that's why the 010 is the best combination that we have here. Okay, so hope that is clear to whoever is attending this talk. Now the thing is, although you were able to solve this thing just by putting all these values in your mathematical expression, you can do it in your pen and paper. Probably for bigger binary polynomials, you may need a computer which will basically iterate through all the combinations that is possible and finally give you the best result by sorting the energy or the value of the function. Now the thing is, even if you are able to solve this in your hand, you won't be directly able to solve it using quantum computer. The first thing, the quantum computer won't be able to understand this mathematical expression, whatever the expression is. So even if you are having only 3 terms here in the expression, the quantum computer will not be able to understand that thing. So for that thing, you have to convert the expression into a quantum native form, which is a Hamiltonian. So now the thing is, what is a Hamiltonian, right? Uh, so I think people whoever are here, so they are coming from different diverse backgrounds. So they may not be having the concept of what is exactly Hamiltonian, but still, I just try to give a brief idea of it. I think that will definitely help all of you to have some understanding of what a Hamiltonian is. So Hamiltonian is basically a mathematical structure which talks about the energy of the system. So what is the system here? So you can see the system is having 3 variables here. That is x0, x1, and x2. So these are the 3 things that you have here. So these are the 3 variables. So your system is having 3 variables, right? And all the variables are binary. So either they can have either 0 or 1. So now the thing is, so if you just want to have a Hamiltonian of it, so definitely we have to do some kind of a conversion of this on this mathematical expression and we'll get it. But before that, so the Hamiltonian is basically a mathematical expression which is which says about the energy of it. Okay, so there are 2 parts of it. One is the kinetic energy, that is the T, and another is the potential energy that you have. So, and here we are talking about quantum systems because a quantum computer is basically a quantum system which can be programmed in such a way so that it can solve your problem. Okay, and your problem is this problem that you want to solve. Your problem is this binary optimization problem or binary polynomial that you actually have. Okay, so so now in a quantum computer, what is a qubit, right? So I think in the previous sessions, whoever the speakers were, so they have already discussed about what is qubit. So I'll not be taking much time that what are the properties of qubit and what not. So, but in a very simplistic way, I would try to provide some kind of intuition of it, what is that qubit is. So, so you can see that qubit is basically considered a simplified view of qubit can be thought of as a bar magnets. So where the bar magnets are having north and south pole. So if that bar magnet is north up, you can consider that to be a up state, okay, or a 0 state, okay. And if the north is down, S is up, you can consider that to be a 1 state, okay. So basically, so what are these states are actually? So I think there is a concept called spin. So the spin, basically I'm talking about Pauli spin. So Pauli spin is having 3 components of it. So this is vector quantity. So sigma z, sigma x, and sigma y. So if we just consider sigma z, so and basically sigma z matrix, and basically try to compute the eigenvector of it. So these are the 2 eigenvectors that we get. Okay, so 0, 0 kit and the 1 kit are 2 eigenvectors of it, which can be also considered as a computational basis. And these are basically 2 possible states of a qubit. I mean, either up spin or down spin, or a one state or zero state. Okay. Now the thing is, how would you program these magnets? Okay, so of course, to program these magnets, you have to, in real life quantum computer, you have to do a lot of hardware engineering, right? Microwave pulses, sometimes lasers, depending on the architecture that you are using. So I won't be going inside those kind of scenario, a very hardware centric kind of thing. Rather, I'll just try to give some understanding of it, how basically you can model your problem, okay, in a way so that your system can understand that, right? So for that, let's have some understanding of it. Get back to your school days, I think. So I think we have all of here, I mean, all the person who are attending this thing. I think they must have played with the magnets in their childhood. So I think that's a very famous game. So when you have two magnets, with one magnet you can't play the game. At least you have to have at least two magnets. So, and we know that the magnets, same pole, basically repulse each other. The force is repulsive, okay, and opposite poles attract each other, okay. And so here you can see this upspin I have mentioned, with two upspins and two downspins. So both will be repulsive in nature, okay. And you have the opposite spins, I mean the opposite poles, those will be basically attractive in nature. And basically, when there's an attraction force, that's called a negative energy kind of stuff is associated with it from the physics perspective. And if it is repulsive, the energy is positive from the physics perspective. Now, the thing is,
Hey, I think I lost the session.
Uh, Team,
Hello.
and yeah, Aniruddha may have facing some problem due to power fluctuation.
Okay.
So let us wait for few more minutes while he is joining. This particular concept I don't know, so I can't explain. But Aniruddha told me to keep the audience engaged. That's the reason why I'm jumping back to the way. Remember, just before this slide, Aniruddha was telling about for various hardware, you will have different approaches, right? Like magnetic pulses or electromagnetic field or laser, those things. So I would like to recall our previous session where we discussed about the physics behind quantum computer, where we explored various hardware platforms for creating qubit, like um, Josephson junction for the superconducting, then optical computer, trapped ion, diamond NV center. So like this, there are various approaches to create quantum bits, qubits. So those, based on those underlying the hardware system, we have to um, initialize those uh, exciting, or what is called those circuits which are manipulating your qubit state from the ONB orthonormal basis state, which will move them to the superposition state, then keep them in the superposition state and perform various gate operations with superposition using Hadamard, entanglement using CX, CCX, and R rotation, rotation over X, rotation over Y, rotation over Z. These kind of operations will have specific values to those field which are controlling the qubit platform. So this one will help you to recall what Aniruddha was trying to tell before this slide. In general, while Aniruddha is joining back, we can have a discussion or kind of Q&A, or someone will be able to explain what is their experience. I think we don't need that Aniruddha come back. So yeah, Aniruddha, please continue. You can continue where you stopped.
okay, I'm not even sure
Yeah,
that
yeah.
where
I informed all members that you may have interruption, so no problem. You can continue.
Okay.
Cool.
Okay. Yeah, sure. So what was the last thing that I said? Can you just tell me?
You are sharing the magnetic.
forgot.
You are supposed to explain one game. We need two magnets for play the game. That's where you left.
Okay. Yeah. Okay. I really it's bad that I really don't know that what happened to the internet, and actually it happened to the browser. Suddenly I checked that the browser is not even active.
Oh, okay.
Okay.
Now you can
Just
share
wait,
your
let
screen.
me.
So you,
Yeah, just
so I
wait.
think he kept speaking and did not know that he was disconnected.
Yeah, exactly. Yeah. Suddenly I noticed that the browser is not active. Then yeah, just wait.
But I thought that, remember, you told me before starting the session there may be interruption in the power supply, so I will have
Yes.
that. I thought that
It's not
problem.
because of. Yeah. I also thought the same thing, but I thought that suddenly the internet
But
went off. But
anyhow,
that's
since
not the
he
case.
pre-wired me, I am able to engage. Please go ahead, Aniruddha. I know you are in the
Yes.
tight time schedule. Please go ahead.
Mm, okay. I have to share the screen first, and then only probably I'll be able to. Okay, just let me know that when the screen is visible.
Not yet.
Mm, yeah. It takes a lot of time.
So while it's loading, you can tell us the game because we are interested to hear the game. We are still child.
Yeah. So is it visible to everyone now?
Yes, it's visible.
Yep. Yes.
Yes. Sorry for this interruption. Let me get back to my thing. So what I was talking about is suppose we have a magnet. So you can see that I'm having one here. So this is a pen. Okay, so I have another pen. Okay, so the concept is basically that two. So you can think that this pointed head is basically a north pole. Okay, so if both are in north pole, so it will repel each other. Okay, so if both are in the south pole facing each other, so they also repel each other. But if they are basically north and south, so definitely they'll be attracting each other, right? So basically, and the force of that attraction depends upon the and it varies to the inverse square of the distance that in between these two. Okay, so whatever. So if there are two spins or the two qubits, if they are an up, okay, so you can think that they are basically up magnets, okay, and if you can think of both the things as down magnet, and if this is the scenario that you can say one up is one down, okay. And what I just told you that if the force is repulsive in nature, that means if the energy is positive, and if the force is attractive in nature, the energy is negative, right? And you can see the mathematical expression of the how the force varies like this, and the energy also varies in this form. Okay, when I'm talking about the force, I'm not force is a vector quantity. It can be attractive and or repulsive. So I'll not be talking about the direction of the force because that is not something what we want to talk about. But rather we'll just mostly talk about this one, that the energy basically varies 1 by r. Okay, so you can see on the right hand side I have added a couple of things here, couple of magnets. This this one. So all are different uh, spins in the up down in terms of direction, but all are having the same distance in between. So you can think the value of the energy will be pretty same. Probably it may change depending on the plus sign or minus sign depending upon the orientation of them, right? So what is the target that we have? The target is that we have a problem. We have this problem that we want to solve. But the thing is, our quantum computer will not be able to understand this thing. So we want to convert them into such a form so that a quantum system can understand. So quantum system is basically magnets, basically qubits. Qubits are basically spins you can consider. Those can be simplified as some magnets with some orientations up or down, okay, following the computational basis of 0 and 1. And these are basically kind of interaction they do possess, okay. Now the thing is, and that's a good thing is that you can control the energy interaction between these two magnets by changing the distance between them. So that's a very interesting part, okay. Now the thing is, uh, when a qubit is there, you really don't know that whether that is in zero state or in one state if it is in superposition, right? So that's why the superposition state I have mentioned or showed here with up arrow and down arrow both because it can be either up or down. Okay, I'm not sure, so that's why the arrow is having two heads, like up as well as down. Okay, so my problem was having three variables, right? X0, X1, and X2. And here basically what I have to convert them into three possible spins. So that is sigma 0, sigma 1, and sigma 2. You can consider. Okay, so let's not use. So this one, and this one. Okay, now the thing is, you had a specific value here in the this particular coefficient. Okay, so every single terms at x square, x0 square, x1 square, or even this quadratic term x1, x0, x1, x1, x2, these are having some kind of terms here in front, right? So now those terms you have to implement here as well, right? So how would you implement that thing? Okay, now the thing is, firstly, I'll just use a specific mathematical formula, okay, which will convert the mathematical expression into another mathematical expression, and then again come back to this one. Okay, so now let's go back to my old slide that I'm having. Okay, so you can see that this is the mathematical expression that you had. Now you are basically applying some mathematical formula, which is basically xi is equal to sigma I plus 1 by 2. Okay, so I'm just not saying about the superscript that I'm having, z. So that is uniform because that's a 1D problem. So here you have x0, x1, and x2. For each of this one, you can replace it with sigma 1, sigma naught plus 1 by 2, sigma 1 plus 1 by 2, sigma 2 plus 1 by 2. And if you do that, you will end up with this expression here on this line. Okay, this is this expression that you will get if you do this kind of a mathematical transformation. Now, what this mathematical transformation is all about, right? And now you had expression and you have now this expression, and I'm saying that this is a quantum native model. How this can be a quantum native model? Okay, so let's go back to the slides, this notepad again. Okay,
So I'm a bit confused how got the sigma 1 and the x relationship.
yeah, okay, sure. Okay, so you can see that formula that we are using, that is xi is equal to sigma I plus z by 1, okay, by 2. So this is the thing. So what was the values, possible values for x? That is 0 and 1. Okay, for sigma iz, the possible values are -1 and +1. Okay, how this is possible? So let's consider that. Okay, so let's simplify it. Okay, so sigma I, sorry, sigma iz is how, what, 2xi minus 1, right? If you just simplify this expression. Okay, and now if you just put 0, let's put xi equal to 0. If you just put xi equal to 0, you get sigma I equal to -1, sorry, +1. Is it? Okay, sorry, it is -1. -1. And if you just put xi equal to 1, you can get this is equal to +1. Okay, so basically you are changing the basis of the problem. Initially your problem was in 0, 1 basis. Now your problem will be on plus minus basis, ±1 basis. Okay, so is that clear?
Yes.
Yeah. So okay, so now the thing is, you have done this basic conversion, and by doing it you have converted the form into this one. Now the thing is, this is basically something called Ising Hamiltonian format. But now the thing is, how would you implement that thing? Okay, just for the, it's a very simplistic scenario. You know, the energy of these magnets or the spins depends upon the distance. Okay, whatever I'm saying, this is a very simplified version of the how the interaction of the qubit actually happens in the hardware. So don't consider this as absolute thing. Okay, but this is just an example of it. Okay, so now you have three different spins or three different magnets, right? You have, okay, so this sigma naught, sigma 1, and sigma 2. And what you can do, you have specific terms here, right? You can see these terms are here in terms of on the top of in front of sigma naught, you have 1 point minus 1.5. In front of sigma 1, you have 0.8. and from term sigma 2, you have 1.2, and for sigma naught, sigma 1, you have 0.7, sigma 1, sigma 2, you have minus 0.2. Okay, so let's talk about these two things first, this last two things first. Okay, and then I'll come to these three terms that we have additionally. So this last two terms that we have, okay, so these are basically some cross terms where basically sigma naught, sigma 1 and sigma 1, sigma 2s are there. So now you know the energy between the two spins or the two magnets varies with the distance. So and you can tune up the distance to get the specific energy interaction, right? So so if you have a mathematical formula, or you must have calibrated your hardware already. So if this is the distance, this will be the energy. If this is the distance, this will be the energy, right? Now the thing is, you want to attain this energy. What is the value of the energy? This value of the energy is 0.7 plus 0.7. Okay, plus 0.7. Now to attain plus 0.7, you can tune up your distance in such a way so that the energy between these two spins will be plus 0.7. Okay, and the same way you can do for the second two spins as well, like sigma 1, sigma 2, that is minus. Okay, that is minus. So the same way you can do the same thing between R12, you can adjust in such a way so that the energy between your sigma 1 and sigma 2 becomes what, minus 0.2, right? Minus 0.2, yeah, minus 0.2 was your the value between in between these two spins. Okay, and for our problem, the interaction between uh, sigma naught and sigma 2, there is no such term in the mathematical expression that we are having, right? Sigma naught, sigma 2, there is not a term that we have. So it means that so you can just keep these two things, this sigma naught and sigma 2, at a long distance, okay, and convert them into a linear chain. Okay, so this is your sigma naught, this is your sigma 1, and this is your sigma 2. This in this way. So this two will be having some interaction, these two will be having some interaction, this one and this one, as they are sitting at the farthest corner, they will be having very less interaction, which basically simplifies your problem. Now the thing is, if you are able to set up this energy expression, okay, not completely, now you are able to, just by tuning the distance, you have created a certain situation how you are able to basically implement this particular last two terms of your mathematical function. Okay, so basically some terms of your Hamiltonian. Okay, and what you have to talk about right now, this other three terms. Okay, now these other three terms are bias terms, and they are called bias terms. So how do you implement those terms? Now what you can have, some external magnets that you can have for individual spins, right? Some external magnets. I have named them as external magnet 0, external magnet 1, external magnet 2. Okay. So what you can do, you can just put this external magnet in such a distance, okay, because these external magnets will be interacting with these pins at from a certain distance, and definitely will produce some energy. Now based on the distance, wherever you put this external magnet, you can attain some definitely value. Now by tuning of the distance, you can also attain these values that you have, minus 1.5, 0.8 and minus 0.2, the same way that you have done here for the two spins. Okay, so if you do that thing, so now it means, so if you have all the external magnets and the internal magnets, these three magnets of your problem, they are in proper distance. So you'll be able to represent your problem perfectly. So whatever your problem was, so your problem initially was this, and now your problem is this. Okay, but you have placed your magnets in such a way so that the energy expression between all those magnets becomes this, and so this is something called a Hamiltonian. So what you have done here, you basically have converted your classical problem into a Hamiltonian, quantum Hamiltonian, and this Hamiltonian is native to the quantum architecture, and this Hamiltonian is having a very good name by a scientist. This Hamiltonian is called Ising Hamiltonian, named I think the name of the scientist was Ernst Young. Some Ising, not able to exactly recall the name of the scientist, but this is something called Ising model, and this Ising model is basically native to the quantum hardware that we talk about. Okay, so this is something. So now once this is done, okay, So then, okay, once this is done, so as you know, okay, so once this icing thing is done, then basically you can send your problem to your algorithm, which can be executed on a on a hardware. It can be a gate-based thing or it can be any level-based thing, and you can get the final result. So that's why our today's talk is mostly about these two parts. Okay, so that's why I'll also give some additional example. Okay, so now what the things are? So what are the basic steps? So now what you have done, you had a basic classical objective in terms of binary polynomial. Okay, you applied some mathematical transformation, you converted them into a Ising Hamiltonian. Okay, and once this Ising Hamiltonian is there, you can apply some algorithm. Okay, and once you apply algorithm, you can get the output result in terms of bit string. Zeros and ones, you can get the final output. Okay, I'll not get into the how a quantum algorithm works because that's a separate topic. Is not something that today we wanted to discuss. That you can definitely see on your own, or you can attend any other lecture, which will be happening in the upcoming weeks, I hope. So this is the basic structure of it. So so this is basically something that I wanted to talk about, and this is something which is uniform for all the problems. So that's why I have just mentioned here. This is the basic workflow. You come up with a problem statement, you formulate them as a binary polynomial, cubo. Once you do that thing, after that step, you have to convert that thing into Ising, because Ising is something what a quantum hardware can understand. And once the Ising is there, then the next part will be a gate-based quantum computer or an NLink-based quantum computer, whatever, or a algorithm which can be executed on the algorithm, or it can be executed on the hardware or a simulator, and you can get the result finally. Okay, so this is something that is. So okay, so now I'll be talking about a couple of examples. Okay, very simple examples. Mainly I'm having 3 examples here. So one is a solving Boolean truth table. Okay, another is basically designing a even-odd classifier, and finding a smallest number using the same approach. Okay, so let's come to the first example that we have, solving a Boolean truth table problem. So here, for the Boolean truth table, we have taken a simple Boolean expression, that is something called AND gate, Boolean AND gate. Okay, so okay, before getting to that, so KG, is everything fine till now? Is there any question?
All good. I don't see any chat message or any question in the chat window. I believe that
I
you
think this
can
is a good time to stop. Otherwise, I think I can just take a couple of questions, see if people are having. Otherwise, I'll just go with the examples that I'm having.
yeah, team, feel free to ask question if you have any question. Aniruddha is open to questions.
Yeah.
Yeah, that's a correct break point.
Yeah.
Any question for anyone? And Aniruddha, I have a question in the interest of all people who are attending. The Cubo to Ising model conversion. I remember you explained how a Cubo model can be represented or can be formulated as an Ising model. Can you rephrase that, how that is in the layman term instead of mathematical formulation?
Yeah, okay. So first thing, the mathematical expression is basically you are changing the basis. So initially your basis was a 0-1 basis, and you wanted to convert them into a -1 +1 basis, because spins are having 2 eigenvalues, which is one is +1 and another is -1. And to do that thing, you just took a linear transformation. The linear transformation is this linear transformation. You can see here. Okay.
So
So
xi equal to sigma raised to power z.
Sigma, no, not to the power. This is sigma z. You can consider that is sigma I. So,
Okay, sigma is okay.
Yeah, so that's the mathematical expression. And once you do that thing, you basically convert the expression into the Ising format. So basically the expression that you had in the x format, they becomes in terms of sigma i's, right? So if you had 3 x variables there in your cubo, now you'll be having 3 spin variables in your Ising Hamiltonian. Okay. And definitely you'll be having
for a imagination or visualization, can I visualize this like from one coordination system to another coordination system? Can I consider that?
Yeah, definitely you can consider. So it's a linear transformation. So basically you are changing the coordinate system. So it's a 0-1 basis, you are converting it to -1 +1 basis. So it's a linear transformation. So you can definitely visualize in this way, the way that you mentioned.
Cool. That answered my
So
question.
hope
Yeah.
up to
Thank
this
you.
point, this architecture of the or the workflow of the basic thing is quite clear. So if you want to solve your problem through quantum optimization problem, you have to have a QO that has to be translated into a Ising. Once that is Ising, you can apply a lot of algorithms. Okay, some gate based and link based, or probably many others. Okay. So now for every problem that you want to solve using a quantum optimization approach, the very important part is that to come up with a QO expression. If you have the QO, you can basically convert them into Ising, and you can get the you can execute, apply some algorithm and get the result. Okay. So today I'm having 3 examples. Those examples are definitely not some NP problems. These are very easy problem to solve, but those will definitely give you some idea of how to solve a problem using quantum optimization. And
Yeah.
that is something was the agenda of this talk, the formulation approach. Okay, so let's start with the first example that we are having here. So it's a Boolean AND gate problem. So I
So I
think
have a
here,
question.
yeah, sure.
Sir, as you were telling that you were having a equation and then you created a Hamiltonian and then you represented it in form of a topology of magnetic dipoles. Am I right?
Yeah.
And
Hmm.
now your target would be to find the minimum energy of this energy system, I guess, to find the minimum value of
Yeah,
the
yeah.
equation.
Hmm.
So I want to know that now you have a magnetic dipole system of, for example, 5 or 6 magnets you were having. So how are you going to apply gate operations on it, and like where is the superposition?
Okay. So actually, this thing is comes under the algorithm part of it. Although, but I'll just try to give you a brief idea of it. Okay. So the thing is, what exactly you want? You want at the end the magnets to be either up or in down, right? So at the start of your problem, you really don't know that what is the best configuration that is possible. They can be either up or down. I mean, can be 0 or 1, right? So you can consider those, you have kept those magnets on a fidget spinner, and basically those fidget spinners are spinning. Okay. And you have basically arranged those magnets in such a way, which of course with a certain distance, and the fidget spinner is the magnets are on the top of those fidget spinners, and every magnet is basically spinning, right? They are at a certain topology, and you have applied the external magnets also, so that you can attain the biases, right? Now the fidget spinner that are basically spinning, those are basically not spinning automatically. Let's consider that you have a switch, and just because you have kept the switch on, because of that switch, all the fidget spinner are spinning, and while they are spinning, you have created a certain topology by changing the distance this way, so that you can attain that particular configuration of energy, right? Now what you have to do is the turn of the fidget spinner button. Okay, once you do that thing, after a certain and that is something that you want to find, right? Is that clear? I mean, there are different ways in the hardware perspective. This is something, a visualization perspective, what you can think, how an algorithm works. Okay. And while talking about how the gate operations will be, so basically you can change the phase of something, you can change the amplitude of something by doing the different gate operations. Okay. And while doing this, you can end up with the final result. But this is something very gate native thing. The one that I gave you, the example that I gave you in terms of fidget spinner, those are basically something you can consider of a as a annealing procedure of it, if you know about that.
No, sir, I don't know annealing. I know the other one, the gate operations thing.
Okay, but in the gate also there is something called QAOA, quantum approximate optimization algorithm, right? So that is
Yeah.
a very similar thing how quantum annealing works. Okay, so basically what you do over there, basically you keep on adding layers of some mixer Hamiltonian and the problem Hamiltonian. Okay, and you basically make the make the p very large. P is basically the number of repetition of your system, of your mixer and the problem Hamiltonian. Once you do the p very large, what you get is basically a very slow process of the same thing. And this is basically as same as that, basically that you are turning off the switch of the fidget spinner. Initially they were spinning at the same RPM. Once you switch them off, they basically get a certain orientation after a certain time. Okay, the same thing. So, but the thing is, this depends upon the algorithm that you are using. That is not the topic of the interest for today. Okay. So I think Okay, so if you're having any other question, I think that we can address at the end of this talk. For now, you can consider this. I think otherwise we'll be overshooting the time. Is it fine, KG, if we just continue and just come to the same question at the end?
Yeah, please.
Okay,
Yes,
sure,
please continue.
sir, sure,
Yeah.
sure.
Yeah. Okay. Yeah. So now the problem is basically for any problem that we want to solve. For that, we have to have a cubo form of it, right? So once that is there, we can convert into Ising format using that mathematical transformation. And once that is there, I think then we can apply a lot of algorithms, different algorithms. So you can see that this is basically a Boolean AND gate expression, right? And this is the truth table of it. So the truth table says that 0, 0 is equal to 0. Basically, AND gate is basically a multiplication gate. So 0, 0, if you multiply, you get 0. Again, if you put 0, 1, you get 0. For 1, 0, you get 0. And for 1, 1, you get 1 only. So this is the 4 possible states. And 4 possible states and their corresponding outcomes, right? Now the thing is how to solve this problem using a quantum optimization approach, right? So to do that thing, uh, of course, some background research is definitely needed that how to construct this cubo. So I'll not get into that thing because that's something that you get after doing a lot of study. Okay, that's an operation research kind of approach. That's a formulation type. But this is something a kind of a cubo you can consider for this same mathematical problem. Okay, so you can see that I have created one mathematical expression or a cubo basically saying the same expression. This is the binary polynomial that we had initially in terms of the f of x0, x1, and x2. This is the binary polynomial for this problem, where I have three variables, binary variables, x0, x1, and y. Okay, and with these three, I have created a mathematical expression which represents the same problem. Okay, how this mathematical expression represents the same problem? Okay, that's why I have added one more table here. You can see. So this table, okay, this table. So here we have three different variables for our problem. Okay, x0, x1, and y. Okay, probably the screen is not visible. Okay, hope this is clear. So this three. So with these three possible bits, because all of this x0, x1, and y, they can take either 0 and 1. So how many states are possible? Is exactly 8. So here you can see the all the 8 possible states I have mentioned here. Okay, from 0, 0, 0 to up to 1, 1, 1. Okay, so now if you just simply put these combinations 0, 0, 0 in this expression, you get the value of this function equal to 0. That's basically energy expression of it. If you simply put 0, 0, 1, you get this. Okay, 3. You just simply you can just do it manually because there are only 8 combinations. You can do this manually. You can change basically replace x1, x1, x0, x1, and y by zeros and ones, one after one. And if you just do the same thing up to 1, 1, 1, you get this. Now the thing is, focus on the truth table first. The truth table is having three binary variables, 0, 0, sorry, x0, x1, and xy, but they are having only 4 possible states. Okay, 4 possible states means 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. Rest of the other 4 are not possible. So which are those 4 possible states here following this truth table? This is the one, because this is the one you can observe here also. Okay, then 0, 1, 0, this is another one that you can also observe here. 0, 1, 0 is available. Okay, then 1, 0, 0, this expression is 1, 0, 0, you can see, and the final last expression, that 1, 1, 1, that you have here. So we are, when we talk about basically simulating an AND gate, we are only interested about these four possible outcomes out among of out of these 8 possible combinations, right? Because with the 3 binary variables we can get 8 possible combinations, but we are only interested about this 4 because this 4 represents the AND gate. Rest of the other doesn't. Okay, because 1, 1, 0 is not a AND gate expression. 0, 1, 1 is not an AND gate expression. This is the OR gate expression, right? And you can see that among these energy values, this red tick combinations are having zero energy, and all the other states are having one energy, or like 1 1 1, and this is also 3. So all the energy states except these four, whatever that you have, are having higher energy, and rest of the others are having lower energy, which is 0. So now the thing is, if we basically execute this problem, okay, into a quantum computer by following either variational quantum eigensolver, QoA, quantum handling, or any other algorithm, definitely this algorithm will be giving us these four possible combinations, because these are the four possible states, okay, where we are getting the lowest possible energy. And if we do that, if we get these four possible states, this one, this one, this one, and this one, it means that we are able to simulate and get properly. Okay, so I haven't added the results for this particular thing. I have results for the other things as well. So let's come to the other thing that I'm having is a even odd classifier. Okay, so so the problem statement is, suppose you have an array of some n numbers. So for the simplicity, I have taken only 6 numbers, and in these numbers you have some even numbers, some odd numbers, right? The target is you have to come up with which of these numbers are even and which are odd. Okay, so basically you can think of it as a binary classification problem. So one class you can uh, designate with zeros, and one class with 1. Okay, so what will be the problem? So you have to have a you have to have the numbers from first, which is basically inputs of your problem, input of your problem. Here you can see these are 6 numbers that you have. Okay, and then you have to have a cubo. Here the cubo I have thought of is this one. You can think of any other cubo as well. Okay, and finally execute a quantum optimization algorithm, get the best bit string or the lowest energy bit string, and out of that, just because it's a binary classification problem, so we'll be getting bit strings with zeros and ones. We'll basically filter out zeros and the ones based on the position of these elements. Okay, so this is the target. So now if we go to some analysis of the cubo, if you see, so this is the cubo that we have. Okay, so we have a array of numbers which I'm designating by n. Okay, so and ni, nj, these are the ith and the jth element of the array. Okay, so and this is my cubo. Okay, so these numbers can be either even or odd. So I have basically given here one table for all the possible combinations for ni and nj. So you can see that if ni and nj both are even, so ni plus nj becomes also even, and 1 plus ni plus nj, that becomes odd. And if you just put them here in the cubo expression, you get -1. Okay, and the same thing if you do for ni equal to even and nj equal to odd, you get odd, and this expression will be even, and -1 to the power even will be +1. And if you just keep on doing the same thing, you get this possible combinations. For even, you get this is equal to -1. For odd, this you get -1. For even odd, you get +1. So if you just do the same thing for all the terms are present here, you get this cubo. This is the cubo having I mean, this is a 6 cross 6 cubo having +-1. Okay, and this is the upper triangular matrix, because cubos can be represented as a upper triangular matrix. Okay, so now you have the cubo, right? So once you have the cubo, what you can do, you can run your optimization algorithm. Okay, and if you run any of those algorithms, you get a bit string. Here you can see that I have performed the experiment and have also my best possible bit strings. Here you can see I have basically executed this on 3 different algorithms: QoA, variational quantum eigensolver, both on IBM machines, and this D-Wave thing. And you can see this is the best bit string that we are getting. Okay, 001101. So, and if with 0, 0, first 2 terms are 0, so it means that 56 and 44 will come in a same group, and again the 5th term is also 0. Sorry, yes. So again you will do the same thing. So the 5th term is here is 54. So this 56, 44, and 54 will be in the same class. Here you can see. And the other you can also extract using the ones, 67, 87, and 33. Now you have to do at least a very simple test. Take one element from any of this group and test by a classical method whether that is a even or odd by dividing it by 2. You can test it, and once you basically do that, if one of your sample of any group is odd, the whole group is odd, and the same is for the events as well. So this is the way that how you can design a binary classifier using a quantum optimization approach. Okay, so let's come to the another example. Okay, is finding the smallest element. So this is a little complicated than the previous one. Okay, so I mean, here you can see that I have an array of elements. Okay, 17, 3, and 49. Just by looking into it, it's quite clear that 3 is the minimum term. So there is no way of applying quantum algorithms or any classical algorithm here. But the target is just to have a simplistic view of how the problems work and how can you basically have some intuition around it so that you can formulate your problem as a quantum optimization problem and solve it using these algorithms. Okay, so to do that thing, we have also here some algorithmic steps. Get the raw output, construct the QO matrix, and run the QO variational quantum eigensolver algorithm and get the uh, uh, smallest possible number here from the output. Do some after doing some post processing. Now the question is, how can you create a QO for this problem? This is a little bit different, right? So let's come to the notepad that I'm having. Okay, so here you can see. So the expression or the array that we are having here. So this is the array. Okay, there are 3 numbers. I'm designating the number by this n0, n1, and n2. Okay, and now the thing is, we cannot just basically extract the output directly. Okay, so we do have to think little to come up with the objective function. So now the thing is, we are quite clear that if all the numbers are unique, okay, of course this is a condition for this to work. If all the numbers are unique, then there will be one smallest element. There cannot be 2 or more than 5 smallest element in a big array. Okay, if the numbers are unique, there will be one smallest element, and that is the crux of it, that how we are designing the objective function. Okay, so now we can think the objective functions, because my quantum computer can only understand these 3 things. Okay, x0, x1, and x2. Okay, zeros and ones. Okay, so I'll whatever the answer that I can get, that will be in terms of zeros and ones, and from those zeros and one, I have to do some post processing to fetch my result. Okay, so here to do that thing, I have created an objective function. So that is basically the dot product between this thing and this thing. So this, if you consider this n to be a vector and this x to be a vector, so what I've thought of is basically constructing an objective function which is a dot product between these 2 vectors. Okay, I shouldn't say it like a dot product. Okay, so okay, basically these are not vector, but I can consider them vector for this particular thing. So if I do this, so I'll get n0 x0, n1 x1, n2 x2. Okay, now this is my objective function, and as we know that quantum hardwares are quite good for handling quadratic structure of objective function. So the final objective will be squaring them up and get the final objective function. Okay, now the thing is, how do we want to get the extract the results? So our result will be coming in terms of zeros and ones. So we have 3 numbers. So to represent those 3 numbers, we are representing them as a 3 bits. Okay, 3 bits, x0, x1, and x2. Okay, now the thing is, with 3 bits, how many states are possible? These are the 8 possible states we have seen already, from 000 to 111. Now the thing is, the smallest number can be only one number, right? So it means, so if I basically designate the locations of these numbers by 1 corresponding to this uh, binary bit string, so it means that these states are only relevant to my problem. Okay, it means if 49 is the smallest number, which is not, then this will be the possible state 001. Third term is 1 here, which means the 49 is my smallest number. Okay, And if let's consider the 3 is my smallest number, then this should be my possible outcome. Okay, 0, 1, 0. The middle of the middle, I mean x1, which is standing at the middle of these 3 bits is 1. It means that we are selecting, we are pointing out towards this 3. And if for our problem this 17 is the smallest number, then this will be our output. Okay, so it means, so there are 3 possible numbers. For each of these possible numbers, we have a one-to-one bit string which maps a number to the bit string, right? And rest of the other bit strings 000, 110, 101, 011, 111, they are not even relevant to the problem, this particular problem, because this problem, the thing that we're trying to find is the smallest number. A problem cannot have two smallest number, right? So for this thing, so here you can see where two bits are 1, that bit string is a not valid answer. The same thing happens for the 3 ones. Okay, so that's why we have to also put a constraint. So what is my constraint? So this is my solution space, right? So this is my solution space. So in this solution space, basically target solution space, one of this bit will be 1. So it means, so for all these 3 bit strings, sum of all the bits equal to 1. So that's why I have added a constraint here, you can see. So this is the constraints that I have kept here, that x1 plus x2 plus x not equal to 1. Okay, so it means if I apply this constraint to my system, which will forcefully search this problem space only, which will not look for the other states that we are having here, although which seems feasible, but not feasible in terms of the problem statement. Okay. Now, if we if we basically combine this objective and this constraint, we get this expression. Okay. So we are basically squaring up, because that the quantum adver can act on quadratic interactions, as we have already discussed in the Ising model. So this is the first objective. This is something that we want to minimize. Okay, minimize, and this is the constraint. Okay, so to add the constraints, we have added a Lagrange parameter, which is basically to tune up the strength of the constraint, okay, that we are having. Now this is basically something, a kind of ad hoc approach. So for my problem, I'm considering that value of the Lagrange parameter is equal to the summation of the square of the individual terms that is available in this array. Okay, if you do this thing, we get this objective function, this QO. This is the QO that we get, which is a very big number, but a hardware basically scales it up within -1 to +1, -2 to +2. Okay, once you have this QO, basically you can execute ending algorithm or a circuit based algorithm. And I have also done the same thing here. You can see on the right hand side, the results are here. The QA, VQV, simulated annealing and quantum annealing, both the results are available. You can see here the best result that we got for all the solvers, that is 0, 1, 0, which means 0, 1, 0 is basically we are pointing out to the number 3, which is actually the smallest number of the problem. So, and if we just simply so this is the final output that we are having. So this is the third example that I had. So now how to basically, so these are 3 examples which basically shows you that how can you formulate your problem as a quantum optimization problem. And once you formulate the problem as a QO, so you can basically apply a lot of algorithms, hybrid, quantum, or completely quantum algorithms to get your final result. Now, how to get started with these things? So where can we get some more references? Okay, so okay, before the references, what are the tool sets that you can use? So there are a couple of tool sets which basically helps you to directly map your problem into a QO without much deeper understanding of the individual problem. Because here you can see when I showed you these problems, the expression of the QO that I derived it on my own. The same thing I did for this one. Okay, but this is a little bit tedious. Okay, now these tools, DWave, CQM, JIJ is having a JIJ modeling by GZept, PyQO, there is something called Amplify SDK. These are something which are Python based tool, and they can help you to formulating a problem as a QBO problem. I mean, not necessarily QBO, there can be other problems as well. I mean, higher order binary optimization polynomial, HOBO, PUBO problems are also there. So these are the problems. These are the tools that where by using them, you can easily convert your problem into a QBO problem. Once you are good with the QBO, then you can use your any optimization algorithm to get the result. Okay, the same. So now, but if you just want to have a study guide, so there are a couple of papers around it. So I think the best paper I could find was Ising formulation of many NP problems. Although this talks about most NP class of problems, the examples that I gave you, those are not NP class of problems specifically, except the TSP thing. So where you can get, I think, almost 21 problems are there where the author has tried to formulate them as a Ising problem or a QBO problem. And you can also read my articles which are there in the Medium. Okay, and just finding the smallest number of the array as well as the even odd classification thing, the examples that I have given here, and you can get the same kind of thing. And thank you. So if you have any questions, you can ask me. I think thanks.
Amazing, Aniruddha. This is something we try to here. This is the lecture I'm telling you. This is the session what personally I am looking for. Understanding the Ising model. The last paper what you have shared is something. Oh my God, this is what I'm looking for.
Okay.
Because those who are working in the Ising model, they know at even any number of times the problem. Oh my God, how it is formulating. You clearly explained with the flow, everything. That is amazing. In my experience, this is one of the highly deep and useful, insightful session. Thanks, Aniruddha. Yeah, over to you, Deepa, for the vote of thanks. And
yeah,
there is
if
a
any
question of
questions are there,
question and
you
answer
can ask
session.
me.
Anyone have any question?
Yeah, if any
Yeah,
questions
please.
is there, I'll be happy to take those.
Hello.
Yeah, hi.
Hello.
Deepa, let us wait for Q&A. There is one question from Dinesh Kumar, especially the conversion to Ising and how to represent qubits with the different. Yeah, Dinesh also seconding my opinion. That's thanks, Dinesh. Yeah, I can connect. Yeah. Stop my camera, sorry. Yeah, Abdullah is telling something, asking something. A nice presentation.
Thanks.
Katie, somebody else was asking question. Yes. Soumya.
Yeah.
Yeah, Soumya, please
hello,
go ahead.
good evening. Yeah.
Yeah.
Aniruddha, it was a very nice and informative session. Thing is, I just wanted to know if there are any sort of optimization problems or that we can use in the energy sector.
Okay. Energy sector. I think recently, I think a month or two back, I saw one competition or one paper which came out of a competition. It was basically energy grid optimization, something which is directly related to the optimization thing. And I think battery optimization people are talking about a lot. But the thing is, I think quite native to the chemical or the material science industry. If I'm not wrong.
Yes, that is one.
I think another is I think the charging station placement is something. I think when the EVs are basically booming.
Yeah,
so charging
more.
station
Yeah.
you can think of.
Yeah, more on EV is. I guess now it is going on. So anything in one more thing I wanted to know. When we do this gate-based approach and annealing-based approach to optimize, is there any specific reasons or or we can use any of them?
Okay, yeah. So here a nice question to address. Yeah, reasons are there. I mean, it depends upon what exactly. I mean, first thing, the budget is a big concern, At this stage, I think the quantum computers are free to use. You can easily have 1 minute,
Yeah,
2 minute access. So if we just simply keep
exactly.
that thing apart. So if your problem is optimization, uh, so you have to check that which players are there. In the optimization space,
Yeah.
D-Wave is a very big name, you can see. And
Yes. Yeah.
there are having 5,000 qubit machines, or probably even more than that. So they do say
Yeah.
that their hardware is very good for optimization problems. And real life
Okay.
optimization problems, the one that I showed you, those are basically very toy level examples to give you some understanding of it. Okay. But the real life optimization problems, so if you're doing, let's consider if you're doing your scheduling problem, work scheduling problem,
Hmm.
and or a paint
Hmm.
shop optimization problem. So these are very big problems. So they do have thousands of variables or even hundreds of variables, right? Now, hundreds
Hmm.
of
Hmm.
variables
Hmm.
you cannot address within a gate-based computer right away, right now. Okay, the gate-based devices are
Correct.
pretty simple.
Correct.
Okay, so for those things you can think of, I think D-Wave kind of things are at least for good for now, because unless the gate-based quantum computer scales up to that particular big size, but otherwise
Okay.
there are gate-based algorithms also, they are quite good. But the thing is, if you talk about the specialization, I think D-Wave is
Yeah.
very specialized in the optimization side. I think it's better to go for the optimization problem in handling devices if you talk about optimization. But also you can try,
Okay.
because IBM gate-based devices are also like improving day by day. So I think in a year or two you may see good improvements on the gate-based devices as well for optimization problems.
Yeah. Yeah, that's it. Thank you.
Yeah, thanks.
If no more questions, I request all of you, please share your feedback. Deepa, you can deliver the vote of thanks, please. Go ahead.
Okay, KG. Before that, shall we have a screenshot of all the participants? Will you please on your cameras?
Unfortunately, I can't turn on my camera, please, because I'm in.
It's fine, KG.
Yeah, the slides and then video will be shared in the YouTube and then our OneDrive folder. You can get it. Diwal and Abdoli.
Okay, thank you.
Thanks everyone. Thanks for
And
joining.
just a minute.
Yeah, sure.
Okay. Okay, here I am, Deepa. Good evening, all. Thank you for all of you joining us for this enlightening section on quantum optimization. Special thanks to our esteemed speaker, Mr. Aniruddha, for sharing his expertise in this fascinating field. We also appreciate the interactive and engaging manner in which you conducted this section, encouraging questions and fostering a collaborative learning environment. Thank you, Aniruddha. We extend our gratitude and appreciation to the active participation and insightful questions from the attendees, making this section truly engaging and productive. Thanks to my PT2 members for their efforts and support in making this section a successful one. And let's continue to explore the potential of quantum computing and embrace innovation with enthusiasm. Thank you, one and all. Looking forward for another wonderful section. Bye, team.
Thanks everyone. Bye.
Thank you. Thanks to all. Thanks, Aniruddha. Bye-bye.